So, in the last lecture we have seen that how that some polynomials we get and we can do or we can perform computation or under modular polynomial arithmetic. Now, our main objective is that how one field can be constructed under modular polynomial arithmetic, even that normal modular arithmetic, that is not a field, and Z8 and Z2 to the power 3 is the example we have given. So, we continue our lecture on modular polynomial arithmetic. And there mainly, if I summarize the last lecture what we have read, we have two polynomials f x and g x, and if I divide that thing by a irreducible polynomial of degree n and we get the remainder r x, then we will be working on this set r x, because r x is of degree n minus 1, since m x has degree n, irreducible polynomial. So, r x must be less than n, that means less than or equal to n minus 1, degree less than or equal to n minus 1. So, first we see one example that how we do this division, because in previous lecture we have seen that addition and multiplication and subtraction. So, now we see the how we can divide and take the remainder. Okay. So, we are taking one example where we choose the irreducible polynomial, where we work in it is of Galois field of g f 2 to the power 8. So, we have to take a m x is an irreducible polynomial of degree n, that means here n equal to 8, p to the power n. So, polynomial of degree 8, because we told that we are forming the field g f p to the power n. So, p equal to 2, n equal to 8. Okay. So, first we choose the m x. Now, there are many irreducible polynomial of degree 8. We choose here one very popular irreducible polynomial of degree 8. Normally, this is used in the standard algorithm of AES in cryptography. So, we choose m x equal to x to the power 8 plus x 4 x to the power 3 plus x plus 1. This is one of the irreducible polynomial. There are many irreducible polynomials of degree 8. So, we take one irreducible polynomial here and we take f x. Now, we have two polynomials with less than degree less than 8. So, let f x equal to x to the power 6. Take the two polynomials, f x equal to x to the power 6 plus x to the power 4 plus x square plus x plus 1, and g x is x to the power 7 plus x plus 1. We remember that my mx, again I repeat, mx is x to the power 8 plus x to the power 4 plus x cube plus x plus 1. Now, we have to do fx into gx modulo mx. So, first we multiply, because we want to compute since we are doing the modular polynomial arithmetic. So, we want to compute Rx, which is equal to the fx into gx modulo mx. So, first we have to multiply. Okay. So, we multiply fx into gx. See, fx is x to the power 6 plus x to the power 4 plus x square plus x plus 1, and x to the power 7 plus x plus 1. So, if I just multiply, normal multiplication this is. So, x to the power 13 if I multiply with x to the power 7 plus x to the power 11, x to the power 9, x to the power 8 plus x to the power 7. Now, I write in the x term that x to the power 7 plus x to the power 5 plus x cube plus x square plus x, 1 is left. So, 1 into this means the fx only. So, x to the power 6, x to the power 4, x square plus x plus 1. Now, see, the coefficients are either 1 or 0, because that it is, we are considering 2 to the power 8, that means my p is 2. If we remember, my field is, I am taking z 2 to the power 8. So, my p equal to 2, that means it will be in 0 and 1, zp is z2. So, z2 is 0, z2 is 0 or 1. So, that means my coefficients can be either, that means my a can be either 0 or 1. Now, if I take, since it is z2, so the my addition will, this computation will be coefficients when we will be taking. So, one thing we remember, the coefficients or the arithmetic on coefficients is under modulo p, that means here modulo 2, that means mod 2 addition and multiplication will be doing. So, here I will be doing, here it will be modulo 2 addition and multiplication. So, what will happen? That means, if I take, it will be x to the power 13 will be there, x to the power 11, x to the power 9, x to the power 8, but see x to the power 7 and 7, since 1 plus 1 is 0. So, there will be no x to the power 7 term, because it is modulo 2. So, 2 plus 2 modulo 2 is 0. So, there will be no x to the power 7. Now, x to the power 6, x to the power 5, x 4, x cube Now again one x square and x, so another 2x square and 2x, so it will be 0, so only 1. So this is the product. So my product is, this is my product is 1 plus x cube plus x 4 plus x 5 plus x 6 x 8 x 9 11 x to the power 11 and x to the power 13. And we remember that the coefficients, the arithmetic we are following for coefficients, then that is modulo 2 addition and multiplication, since p is 2 here. Modulo 2, since I have written since p equal to 2. Now we have to divide. So if I divide by mx, now I have to do fx into gx divide by mx, because rx is the remainder we have to take. So if I do that thing, we remember our mx is x to the power 8 plus x 4 plus x cube plus x plus 1. Now we divide, and my product fx into gx is x to the power 13, x to the power 11, x to the power 9, x to the power 8, x to the power 6, 5, x to the power 4 plus x cube plus 1. So now polynomial I have, it is 8 and 13. So if I multiply by 5, my quotient is 5, then I can get x to the power 13. See 4 plus 5, I have x to the power 9. So I have, okay, I write, since I have one x to the power 9 term, so I can write here x to the power 9, then x to the power 8, I have x to the power 6 also, and I have x to the power 5. So that this is normal addition, and since under modulo 2 addition, the addition and subtraction are same. So that is why we are not using any minus sign. We write that under modulo 2 addition and subtraction are same. So we are not using any minus sign. So it is only x to the power, it is only x to the power 11. Then these will all cancel out, then x to the power 4 plus x cube plus 1. So since x to the power 8, so I can take x to the power 3. So it will be x to the power 11, then see x to the power 7. So I do not have any x to the power 7 term. So I write x to the power 7 here, x to the power 6, I do not have any x to the power 6 term, then x to the power 4, I write x to the power 4, then x cube. So again if I give, I get x to the power 7, x to the power 6 plus 1. Now see that mx is of degree 8 and I get some remainder Rx. So this is my Rx, I get some Rx equal to x to the power 7 plus x to the power 6 plus 1, whose degree less than equal to degree less than 8, degree less than 8, that means the degree of mx, 8 is the degree of mx. So this is my, this is the, how we can form the remainder. So this is modular polynomial arithmetic. So now we can use, instead of this, that means my, what it becomes, that I can write that Rx, I compute Rx is fx into Gx modulo Mx, and I got this for these fx and Gx value. Here my Rx is, I am getting Rx is x to the power 7 plus x to the power 6 plus 1. So, the similar to my polynomial arithmetic, normal modular arithmetic, I got the modular polynomial arithmetic. Now, we will be using this thing to form a field. Okay. Now, we take our p is 2 and a 2 degree polynomial we take. That means, z, okay, we take one example and how we can example that forming a field in Z22. That means, when we are telling Zp to the power n, that p equal to 2, n equal to 2. So, again first we see what are the polynomials, because p equal to 2 means it is in Z2. So, that is 0 and 1, coefficients can be only 0 and 1, and it is n equal to 2. So, my polynomial is fx is a1x plus a0, only 2 values. We know that all possible values of a1 and a0, that means a1 is 0, can take 0 0, 0 1, 1 0, 1 1, these are the 4 values, the way we have represented. So, my fx, I can directly write that fx, the set of fx, better I write the polynomials, the set, the set of polynomials S consists of the polynomials 0 0 means 0, then 0 1 which is 1, then x and 1 plus x. So, these are the, this is my polynomial set, that means S is 0, 1, x and 1 plus x. So, these are my 4 polynomials. Now, we remember that when we will be coefficients, for coefficients arithmetic will be for coefficients arithmetic, that it is the under modulo 2 addition, because modulo 2 addition and multiplication and for the set of polynomials, for polynomials arithmetic we will be considering, for polynomial arithmetic we will be considering modulo mx, where here is of, since they are less degree 1. So, mx is of modulo mx, mx is irreducible polynomial of degree 2. So, if we just do that thing, that we know that for degree 2 there are only 2 irreducible polynomials. I take 1 plus x square, mx equal to, I take this is one irreducible polynomials. Now, if we do the addition and modulo addition and multiplication table. So, if I consider addition and multiplication table, so this is modulo mx addition table. I have 0, 1, x and x plus 1. These are my 4 polynomials: 0, 1, x and x plus 1, 4 polynomials. I am doing modulo addition. So, 0 plus 0, it is 0, 0 plus 1, 1, x, x plus 1, simple modular simple polynomial addition. 1 plus 0, 1. Now, 1 plus 1, 2, and this becomes 0 because it is modulo 2 addition. So, it is 0. Now, 1 plus x. Now, 1 plus x plus 1. So, x plus 1 plus 1 2 because coefficient arithmetic is modulo 2. So, this becomes x because 1 plus 1 cancelled. Then x plus 0 x, x plus 1 x plus 1, x plus s again it will cancel. Then x plus 1, this becomes 1, x plus 1, then this is x, this is 1, this is 0. Now, we see 0 plus 0 0, 1 plus 1 that is 0, x plus x 0, x plus 1 plus x plus 1 0, and 0 is the additive identity. So, 0 is additive identity and x is itself the additive inverse, self the additive inverse of x, additive inverse of x. Now, if I consider modulo mx multiplication. Okay. So, we consider now modulo mx multiplication table. Now, for multiplication, if the product becomes the degree is greater than the n, here it is 2 1 multiplication table, then we have to divide by this irreducible polynomial mx and we have to take the remainder. So, again if I do the table, zero, 1, x and x plus 1. Here if I give the modular mx multiplication, I will take 0, 1, x and x plus 1. So, 0 if I multiply the coefficients, so it will be non arithmetic modulo 2. So, it will be 0 only, 0 only. 1 if I multiply, then the number itself. So, 1 into x x, 1 into x plus 1, Now, x into 0, this will be 0, x into 1, this is x. Now, x into x, this becomes x square. Now, see, I do not have any x square in this element, because that my, if I remember that my set was S was 0, 1, x and x plus 1. I do not have any x square, because the degree 2 is greater than this mx has degree 2. So, I have to divide x square by 1 plus x square, and if I do that thing, just we will be getting that if I divide x square, if I divide x square by 1 plus or x square plus x plus 1 mx, then I will be getting 1 and this becomes x square plus x plus 1. So, the remainder is x plus 1. So, I will be giving this remainder, instead of x square I will take the remainder, this is x plus 1, that is modulo mx we are doing. Similarly, if it is x square plus 1, and now we understand that if I divide by x square plus x plus 1, so simply the x square plus 1 will go. So, this becomes x. Similarly, now it is 0, it is x plus 1, and here x into x plus 1 is x into x plus 1 is x square plus x, and if I take modulo x square plus x plus 1 my mx, then if I divide, simply x square plus x and x square plus x will vanish. So, it will be 1, and now if I multiply x plus 1 into x plus 1, then x plus 1 into x plus 1, this becomes x square plus x plus 1 is x square plus 1. Again this is degree is more. So, I have to take modulo x square plus x plus 1, and then x square plus 1 will go and x I will get. Now, we see that if here it was multiplicative identity, additive identity was 0. Here we see that other than 0, the way we have defined, we have for 1 we got multiplicative identity 1, for x square, this will be 1, because x square plus x, so 1 will be there 1. So, I get multiplicative inverse identity 1, here also I get 1. That means, here my additive identity it was there, and similarly here I get my multiplicative identity, for all elements other than 0 exist, and that is equal to 1. So, I have multiplicative inverse for all element other than 0, because I am getting 1, because for 1 multiplicative inverse is 1, for x multiplicative inverse is x plus 1, for x plus 1 multiplicative inverse is x, because x into x plus 1 equal to 1. Since I can write for x into say x into x plus 1 equal to 1. So, multiplicative inverse of x is x plus 1, or the reverse multiplicative inverse of x plus 1 is x, and for 1 it is 1 only. So, what we see that the inverse exists. So, that means it will now it will form a field. So, I can conclude that we have taken Z p to the power n z2 square, and the irreducible module mx we have taken 1 plus x square. This is important because selection of different irreducible polynomial will give different results, and but it will that it z2 square, what we see that z2 square means z4. See, it is not a prime, z2 square, it is 4 is not a prime, still z4 forms a field. When we have converted this operation in modular, or computation is modular polynomial arithmetic, and then z4 just now what we seen, even the 4 is not prime. So, what earlier we have seen that in normal arithmetic, normal modular arithmetic, if only ZP forms a field, it is not a prime. But we have, so we have now we take that ZP earlier we have seen forms a field under normal modular arithmetic. And what ZP to the power n forms a field under modular polynomial arithmetic. So, this is the conclusion that we make, that ZP to the power n forms a field. We will continue this lecture with some example we started in the next class.